Alright, so in this video, we basically just gonna convert all this to per unit. Alright, so the first thing that we will have to do before we do anything is choosing our MVA base. So in this case, we will choose 100 for the MVA base. Most of the time, they'll give you what it is. So, bruh. So that the base we'll be using for this. So that's the first thing we have to choose. So the second thing we have to do before analyzing this is the generators. They must be represented in MVA. So this one had to change and this one had to change for sure. So if you're gonna do that, so G1. So thinking about it, right? This is megawatt. So if you have a triangle and you know what this is, and down here is megawatt, and you want here, which is MVA, a little bit of tricks. So this is the adjacent. There's the hypotenuse. So therefore cos theta, which is your power factor, is equal to the adjacent and the hypotenuse. So this is 0.8. The adjacent is 180. And to get each, you can just swap. So it will just be 180 mega divided by 0.8. So that's how we would do that conversion. So for G1, so it will be 180 mega divided by 0.8, and that'll be 225 MVA. The next way to do is G4. So all G4 is same thing, so it'll be G1. This is equal to G4 because it will basically the same 180 power factor 0.8. These two already in MV, so they're good. So that's first step, check. So then we say using MV base of 100, so we had to standardize the system to 100 MV, right? So the first thing you normally start with is your generators. And a middle equation. So right now we'll do the 180 first, and we'll do the 150. Sorry, in this case it will be 180, it will be 225s and the 150s, because these are 225 MV. So we'll do the 225s. So for the 225s, the Z per unit new will equal to the Z per unit old multiplied by the MVA new divided by the MVA old. So in this case, it will be, sorry, this one is 0.03 multiplied by the new MVA, which is 100, divided by the old one, which will be 225, and we will basically end up with 0.0133 J. These are generators G1 and G4. And then for the generators G2 and G3, it'll be the same equation, so just end up being, so the O is 0.02, both of them, MVA new, and the old MVA is 150. So when you multiply that out, you'll basically end up with 0.0133 G. Right? So that are the generators. The next thing we had to get converts to per unit is your transformers. So right now these transformers at 450 at a per unit as 0.4. So we just need to convert the transformers on a whole. So these are different color. So the transformers, so it'll be Z per unit new, what equal to the old, which will be 0.4 multiplied by the new MV divided by the old MV. So you end up with 0.089 G, and those are the transformers. It's the same transformer, so it'll be the same per unit impedance for both of them. If this one had a different Z per unit or a different MV, you would have to change the values in the equation to account for that. And then the other thing we had to convert is the actual impedances for these two lines. If anybody asking why didn't we consider these, it's because the distance so small that it's negligible. Right? If anything, anytime they give you actual impedance, you always have to convert it to per unit. If they don't give it, that means the impedance negligible, so you really have to consider it. So these are the transmission lines. So remember, so ZB, in this case, it will be Z per unit, because we're going to convert it to will equal to the actual divided by the base. So right now we don't know what the base is. We don't know what Z base is. So we had to calculate what the Z base is. So we go in the corner. So Z base, you have two equations for Z base. So the most basic equation is KVB squared on MV base. So in the transmission lines, they go into 69. So in this question here, we will use 69 kV as the MVA base. Sorry, not the MVA, the voltage base. Right? In the question, they'll give you what the voltage base is. So in this case, we'll use 69 as the voltage base. I have no way to know, really, because on this side of the transformer, the voltage base is 11, and on this side of the transformer, the voltage base is 69. So technically, if you're transferring the impedances on both sides, you will have to use a different voltage base, but ideally it will be the same impedance anyway. Right? You'll see more of that when you go into our relays, calculating the timing for relays and stuff and transformers. You'll get that in those. But for now, 69 kV will use that as the voltage base. As I said, they will give you what voltage base to use. Hmm? So in this case, it will be 69 squared divided by 100. So that will be 47.61 J for the impedance base. So now we come back here and we just divide the actual by the base to get it to the per unit. So in this case, in the line, it's 2.38. So we come back here, so it'll be 2.38 divided by the 47.61, and you end up with 0. 0499 G. Right. If anybody asks per unit, the impedance itself is G, but since it's a ratio, you normally don't write the J, but as a rule of thumb, you normally write it, so you wouldn't really lose marks. If Sir said the body J, you go ahead, but for the final answer, you normally put J anyway, so it wouldn't really lose marks if you put it or don't put it. But as I said, some people get a fishy with it, so if you don't want to put it, you don't need to, but for the final answer, make sure you put the G. Okay, still our impedance at the end of the day. So anyway, so that was the transmission lines. So we converted these, and we converted these. So the last thing we have to do is just draw an equivalent circuit for all, for everything basically. But before I do that, I want to calculate something. So the last thing you will need to calculate is something called a current base or I base. So I base is basically a kVA base divided by root 3 of a kV base. So this will give you a current base. So the MVA base is 100. So if you want to convert it to kilo, so it would just be 100 M divided by 1,000. If you want to know how much thousands in it, is that correct? Yeah. And then you divide it by root 3 of 69. Yeah. And that will equal to 100 mega divided by 1 10 to the 3. So you basically end up with 1,000 divided by root 3 by 69. And put in a calculator. Will be 69 multiplied by root 3. Yeah. So I end up with 8.367 amps. That's not. Let me just make sure I do that conversion correct. So converting mega to kilo. Right. So let's see and make sure. Better to be safe than sorry. So it's 100 mega. So you multiply by 1,000. I know that was looking weird because it was kind of weird to me because I was looking real foreign in my book. So 100 mega will basically be 100 by 10 to the 3 based on what the calculator saying 100 by 10 to the 3. Cool. And then when in doubt, always check the good old faithful Google. So it erase all this. So and erase all this, and erase all this. So it'll be 100, 1, 2, 3. So let's see how the answer will change. No. So backspace all that. So it'll be 100, 1, 2, 3 divided by open brackets, square root of 3, and then multiplying that by 69, 836.7. Yeah, so rule of thumb, mega to kilo. Here, multiply by basically about 1,000. Yeah, I learned something today. Cool. Yeah, nice. So that was the IBs. Most of the time you have to calculate the IBs to get other stuff, which is like your fault parent. So for now, we'll leave it there. So I just draw the per unit equivalent circuit. So basically, you're just replacing all the impedances with a resistor, and the G's I could leave it as a generator. So you have 4 generators, 1, 2, 3, and 4. So we have our impedance here, impedance here, impedance, and impedance. Normally we will write the magnitude of the voltage and the current. So for these is always 1 angle 0. And the impedances are the generators. I think all of them was 0.0133. Right, and then that going down to our bus. And then it have 2 transformers. And the per unit impedance of the transformer 0.089, 0.089, and that went down to our bus. And it had the 2 transmission lines. Both of them were 0.0499G. Then those 2 went down to a bus. Then what happened after that? Oh, it just split into 2 loads. Yeah, cool. So this would be the equivalent per unit circuit, not the reduced, because we didn't reduce it. So to calculate faults and stuff, you'll normally have to reduce this entire thing down to 1 generator and 1 equivalent impedance with a load. But the load in this case will be a fault. So that will be the beginning of something called fault analysis, which we'll do in another video. But for now, that's basically how you just get your equivalent circuit, in this case your per unit equivalent circuit. So just a recap from the question, first off, convert everything to MVA, choose a MVA base and a V base, unless it wasn't given to you. Then megawatt MVA. After you get everything in MVA, you convert everything from its old per unit to the new per unit on the base. And if you have any actual impedances like lines and stuff, you calculate the Z base and then you just divide it into the actual to get the per unit. And then when you do all of that, you just come and you just exactly how the circuit looks. The generators, the voltage, angle, and magnitude is always 1 angle 0 when you're drawing the circuit. And then you write in the impedances. These are the impedances of the generators. You go down to the bus, then the transformer, the lines, and your loads. And that'll basically be it. So in the next one, you'll do the fault analysis, which is basically reducing the entire circuit down to a equivalent circuit. Cool. So, good talk.